for 3a, it gives you two distributors, j and k, but a is only talking about distributor j, so we don't have to care about distributor k, which is good because it doesn't tell us anything about distributor k. By the way, this is from the AP Stats test that I took. So, yeah, this is one of the easier kinds of problems that they're going to give you on the FRQ, because it's basically just using normal CDF. Okay, so it gives you that the diameters of the melons from distributor J have mean 133 and standard deviation 5 millimeters. So for this question, it asks, what is the probability that the melon will have a diameter greater than 137 millimeters? So because we're not taking a sample, we don't have to do anything other than use the population parameters that they give us. And that's especially true because we're only looking at one random melon that we're taking. So we can draw the distribution. And say it's 133 as the mean because that's the population mean. And the standard deviation is 5. So multiply like 3, that's 15, add it to this. This is going to be around 148-ish, just to like help us visualize. And so it's asking, what is the probability that a melon will have a diameter greater than 137? So that'll be probably around here. And it's greater than, so we shade the region above. So we have 137, and then mean and standard deviation. So all we have to do is plug it into our calculator. So we'll use normal CDF, and then lower bound, which is 137, upper bound, which is positive infinity, so 1e99, then mean 133, and then standard deviation, which is going to be 5. And then from that, if we calculate, we get .211, which seems fairly reasonable because this is not that much of an area, but it's not super tiny either. Okay, so this is like the easiest kind of question that you're going to get regarding normal distributions and using normal CDF and things like that on the test. Because if you look at this, then you have to deal with two different probabilities because you have a store that buys both distributor J and distributor K's melons, and then you have to deal with the probability, and then you have two different distributions, and then it gets a lot harder. And I just didn't have you do that one because of the probability things. And I'm scared that you don't know it because I didn't cover it. So, yeah. Anybody have questions about A though? You were able to do this theoretically, right? You get the right answer? Good. Alright. So, that's all the warm-up I had. And it's not even that likely that you're going to get a question using normal CDF or any kind of things like that, even sampling distributions on the FRQ, because why would they ask you that when they can ask you to do things like confidence intervals and hypotests, which are the next step of what we're doing after we cover one last thing in sampling distributions. So if you look at the different problems in this test, this asks for confidence interval, and this asks for analysis of confidence intervals. And then we have the normal CDF question here. The first one was the wolf question, like wolf length versus their weight, which we went over earlier, and this is just analyzing visual data. But if you look at other tests, they usually don't have a question like 3A, because this is really easy, and it takes you like 3 minutes most. So, yeah. Don't expect things to be this easy when you actually take the class. Okay, so we have covered what to do if you're given population parameters and also what to do if you're given population parameters and you're taking a sample of them. But we have one more thing to cover with sampling distributions, and that is something you've probably never heard of, which is called a t-distribution. And so I will go over when you should use it and what it is and how you use it. Okay, so this is a screenshot of my previous lecture, and that's saying the conclusions of the central limit theorem, which is saying, like, once you meet the criteria of saying that the sample distribution is greater than 30 and all those things, then you can conclude these things. And it's really helpful if we know what sigma is and we know what mu is, because otherwise we cannot calculate what the standard deviation of the sample is, and we won't be able to figure out what the mean of the sample is if we don't have the data ourselves. So, is it really realistic that we would know the population distribution that well so we could, like, we literally know the population standard deviation? Not really, because if we're analyzing things in statistics, that probably means that we don't know much about it to begin with, unless you're taking a stats class. If you're doing actual research, then you probably don't know what just sigma of the population is. You probably don't know what the mean is, so that's why you run the study. So, but if we don't know what this is, then we can't use the sampling distribution. Also, while I'm on that, there is a difference between your sample's distribution and the sampling distribution. So, your sample's distribution is the data that you collect, and if you put that on a histogram. But your sampling distribution is, it looks like a normal curve, which is why we always describe it as that, but this doesn't look like a histogram because it's not boxy. So we're saying if n was infinity for our sample, then that is our sampling distribution, because the sampling distribution is different than the population distribution. So you have three things. You have your sampling distribution, and then you have your sample, which will probably look something like this, and then you have the population, which looks the same as the sampling one. Maybe. We don't know. It could be normal, or it could not be normal. We went over the fact that the sampling distribution is always going to be normal as long as it's greater than 30 and meets all the other criteria. It doesn't matter what the population distribution is. It can be like this, and then these two, the sampling distribution and the samples distribution, those might be feasible things that you're going to get when you collect the data with this population. So you have three distributions: sampling, the sample, and the population. I didn't cover that before, but that's like something very good to know.
Wait, what's the difference between sampling and sampling?
The sample is literally the data that you collect and put on a histogram. So if you took like infinite samples, then it would be exactly the same as the sampling distribution. But the sampling distribution is totally smooth and normal looking. So the sampling distribution is theoretically what the samples should look like. The population distribution is just the population, and what the sampling distribution looks like is different than what the population looks like. And as you increase n, then your sample is going to look more and more like your sampling distribution. So normal. Okay. Everybody good with that? That's population. All right. So, if we are given descriptions of our sampling distribution, but not the population, and we don't know what this is, but we know what the standard deviation of our sample is, then we can't use this, because this makes it useless, because we don't know what that is, so that formula doesn't work for us. So instead, if you do not know the population standard deviation, then you have to use a t-distribution. And I will go over that. So this will be in practical terms basically all the time, because if you're doing a study, then you don't know the population standard deviation unless you're imitating somebody else's study, in which case, why are you doing that other than to fact check it? But let's talk about when we should use the t-distribution. And then there's criteria on the right, which is thrilling. But, okay. This is, pretend this isn't here for now. We'll go over it later. So, because you can use a t-distribution for both proportions and sample means. So, this whole point is void. Don't care about that. So, the first criteria, or the first thing that indicates to us that we must use a t-distribution instead of a normal one is that we don't know the standard deviation of the population. So we don't know what sigma is. And that'll be most of the time in real life, but probably not most of the time when you're taking a class, because they like to test on both. So, to use the t-distribution, we have to know that the population distribution is normally distributed, or that n is large. So it could be 30 or 40 depending on who you ask. I'm just going to say it's 30 to keep it simple. So if n is greater than 30, then you can use the population distribution. But if n is less than 30, and you know that it's normal, you know that the population is normal, then you can also use the t-distribution. So that makes a lot of the problems that you're going to get in the class doable, because they're not going to give you 30 data points to put on your graphing calculator. They're going to give you like 10. And so if n is less than 30, then you're going to have to use a t-distribution. But we have to know that the population distribution is normal. And sometimes the question will not tell you that. So if they don't tell you that this is normal and it's less than 30, but they give you the data, then you can just make a histogram or a box plot of the data and just check, does it look kind of like this? Because if it looks kind of like this, then you can just say, all right, we're just going to assume the population distribution is normal because the data looks like it's kind of normal. And that is very much a stretch, but you're allowed to do it. But if your data for the question you're doing looks like something like this, then you will be expected to say that we must proceed with caution because the sample that we obtained does not look normal. So you can still use it, but theoretically you're not supposed to, and they expect you to recognize that. So if you get a sample distribution and you don't know that it's normal, that the population is normal, you can look at the data. If the data doesn't show that it's normal, then you can just say proceed with caution. Use a t-distribution. Okay. So let's talk about what the formal criteria are, which is the points that they expect you to show on your work. So the first one is the same SRS, and then the third one is also the same, and is greater or less than 10% of the population. And then the second point is what we went over here. So n has to be either greater than 30, or it can be less than 30, but we check the data. And also one thing that you should put is, we don't know the population standard deviation, so we're going to use a t-distribution instead of a normal one. So these 2 points and this point is the difference between the criteria for t-distributions and normal distributions for samples. Okay. And you should definitely write down on your paper that we don't know sigma, so we're going to use a t-distribution, because otherwise you're implying that you're using the t-distribution, and that may make the graders confused. Okay. So this says that this makes it possible for us to make inferences about data even if our sample is less than 30. And that's really important for what we are going to do later, because 90% of the time, if there's no way they're going to give you 30 data points to put on your graphic calculator, because that just takes too long, and it's a test, and you're going to be struggling for time, and they don't want to check how quickly you can put data into your graphing calculator. They want to see what you can do with that data. So we're going to be using t-distributions a lot. Okay. Anybody have questions about this slide? Oh, this eraser is terrible. Okay. So, remember how I said that a sample standard deviation is denoted by the variable s instead of sigma, right? So that means if you plug in the data into your graphing calculator and like enter one variable stats, s is the thing that you're going to get from that sample. So we didn't use it before because we were talking about sigma sub x bar, which is the sampling distribution's standard deviation. Not the distribution of the data that we're looking at, but the sampling distributions, so the theoretical n equals infinity samples standard deviation. So you have three different terms for standard deviation. So you have sigma, which is the population. You have sigma sub x bar, which is the sampling distribution's standard deviation. And you have s, which is just straight from your data, calculate standard deviation. Okay, so we do not know, if we're using the t-distribution, we don't know this. So we cannot calculate this, because the way we calculated the sampling distribution standard deviation is by using this formula. And since we don't have sigma, we can't find sigma sub x bar. So we can't really use the samples distribution either, because the samples standard deviation depends on how many samples you take. Because if we remember, as n increases, then the distribution becomes slimmer, right? We went over that using the other formula, so we have to do the same thing here. So if we're describing the sampling standard deviation using a t-distribution, we use something called standard error. And this is, you can translate that in your brain to t-distribution standard deviation. And the formula for that is the same as the formula for this, but instead of the population's standard deviation, you use the sample's standard deviation. So before, we went from knowing the population's standard deviation to knowing the sampling distribution's standard deviation. But now we're using the sample's standard deviation to find the sampling distribution's standard deviation. That was a mess of words. So what this formula is saying is we're going from sample to sampling distribution. And what this formula is saying, we're going from population to the sampling distribution. Because all of the questions that you are going to get referring to the sampling distribution are saying, if I take a sample of 50, what are the sampling distribution's qualities? Or they'll give you a normal CDF question about the sampling distribution. So the sample is not that helpful to us on its own, because we cannot conclude anything about the population or the sampling distribution from it. And the population is overly useful to us because that means we understand it fully already. But for some reason, they expect you to go from knowing about the population you're looking at to theoretically, if you took a sample of 50, what would that look like? Yeah.
The question, do they give us the sample distribution?
Do they give you the sample distribution? If you're going to
the
use
sample standard deviation, sir.
They're either going to give you data or they're going to tell you.
Okay.
So they'll give you S, or they'll give you the data that you need to find S using one variable stats on your calculator.
Can you say what's population to sample?
So the formula that's on the way previous slide. So
Oh,
the one that's covered here. So if you see sigmas, then that means you're looking at populations. And if you see SE and S, then that means you're looking at samples. And note that the thing in between basically is the sampling distribution. Okay. Note that, so make sure you're aware of which one you use to describe what distribution, because the sample S only describes the sample distribution, not the sampling distribution. And so you use SE sub x bar and sigma sub x bar, both for the sampling distribution, depending on if you're given sigma or S. And that's pretty clear because they both denote it as sub x bar, which refers to the sampling distribution's mean. And we already know that from previous lectures. Okay. I didn't know this when I took the class. So I didn't know the difference between a sample and a sampling distribution, so it's a miracle that I did well, but I hope I can make it clear to you so you understand it, because I'm learning quite a bit as I review the material to teach. All right, everybody good with this slide? Okay, so let's talk about what the t-distribution actually looks like, because it is a distribution that's different from normal. So basically, if you look at the graph of it, this is the t-distribution here, and it looks really flat. And so the reason why this t-distribution is different from the normal one is that there's less of an increase at the top and less of a decrease at the sides, depending on what n is, because the distribution changes as sample size changes. So for most, so if you had n equals infinity, then it would look like a normal distribution. The t-distribution with n equals infinity equals the normal distribution. But most of the time you're not going to get that. So the peak is going to be shorter than the peak of the normal distributions, and the tails of it, so the furthest left and furthest right, are going to be higher than the tails of the normal distribution. Okay. So if we're describing the distribution of a t-distribution, so for a normal distribution, we only describe it using mean and standard deviation, correct? Like those are the only variables that we use to describe it. We can do all our normal CDF stuff just using the mean and the standard deviation. But for the t-distribution, it's weird. Don't read what I wrote here because that's not the best way of expressing it. So the variable that we look at is df, which stands for degrees of freedom. I don't know why it's called degrees of freedom, but that's what it is. So degrees of freedom is calculated by the formula n minus 1. So your sample size minus 1. So it'll be like 29 or greater, or if it's less than 30, So that is the only thing that you use most of the time, because the calculator functions do not allow you to customize your t-distribution to what the data gives you. So you're not allowed to put in the calculator what your mean is and what your standard deviation is. So instead, what the t-distribution on your graphing calculator allows you to do is standardize it in a way that looks like this. And it only gives you z-scores on the x-axis. So these are standard deviations. These are not the units of the thing you're looking at. And that's something that you need to note, because in the past, we were able to enter the mean and standard deviation to our normal distribution and not have to care because everything's in terms of whatever unit we're looking at. But for this, it does not let you input mean standard deviation, so you have to treat what you get from the calculator as t-scores. So we used z-scores before, and for this it's t-scores. Okay.
What exactly is
It's a measure of how much of a difference there is between this height and this height. So as you increase degrees of freedom, you get closer and closer to standard normal distribution, because I mentioned that if n was infinity, then you would get a normal distribution out of your t distribution. But, so df just represents how squished it looks, basically. And so you're expected to know that as you increase sample size, then your t distribution is going to look more and more like normal. But for most reasonable problems, it's not going to look especially normal, although the shape is generally bell curved and symmetrical, the same way the normal one is. Okay. Does anybody have questions about the calculator thing and standardizing it based on t-scores? Okay. So, this is, okay, and all of the material that I looked at, so you know how we were doing crazy problems with like that one with Jane and the other guy with walking speed? You're not going to get anything like that with, wait, no, that wasn't sampling, but, okay. You're not going to get really hard problems with just using the t-distribution, because the t-distribution is just a tool that we use to do more complicated procedures in stats. So the only thing that I think that I need to teach you is inverse t, which, do we remember what inverse norm does? What does this do? What do you put in? Yeah.
Area.
Put in area.
Mean and standard deviation.
Mean. What does it give you?
The boundary.
It gives you, yeah, the bounds. So, and then it gives you the bounds. So, inverse t does the same thing, except now you have to put in area and degrees of freedom, and not even mean MST, because they don't care. They're going to give you the t-score. And inverse t will also go from left to right. So if you said area is equal to 0.6, then it would show what area that looks like this is equal to 0.6. Okay. And if you want to input it into your calculator, then it's literally just the same as that. I can pull it up. Let's just say that we're using second distribution in the same place that you find normal CDF, and then inverse t. And you do have tPDF and tCDF, but I don't think you're going to use them very much. And if you do use them, then you just have to keep in mind that you're using t-scores and not actual bounds. So let's just do inverse t. And let's do the same problem I just did over there. So I'll put in 0. Let me double check this, because I'm not sure what the order is. Because I do it on my calculator, and okay, it is area, and then comma, your degrees of freedom. So let's say we had a sample that was n equals 35. What is the df for that? 34. So we would put in 34 here as the degrees of freedom. And then that's literally it. That's all you need for the function, and it gives you the z-score for here. Or I mean t-score. So t equals 0.255. Does that make sense to everybody? Okay. On my calculator that shows me everything that I need to put in, I go into tCDF, then it asks for lower upper df paste. So paste is just enter. So it asks for the lower bound, upper bound, and then just df. So this is tCDF. This is going to be the lower bound of using a t-score, not using the data that you're given. So if you're going from left to right, then it would just be negative infinity. But once you get to the upper bound, then you would have to figure out, using the mean and standard deviation of your data, what this value is in terms of standard deviations and not in terms of the units that you're looking at. So if I had mean 25 and standard deviation 5 for our t distribution, and I wanted to find the area beneath, I don't know, 30, then I would have to do 30 minus 25 divided by 5, because that's our t-score formula. So it would be x minus x bar over, that would be SE. So this is mean, this is standard deviation, and this is the thing we're looking at, so it would be 5 over 5 basically. So t would equal 1. And so I would put 1 in here, so this would be negative 1e99, this would be 1, and this would be whatever the sample size is, so 34. We'll just use the same one as the other. So that is what you would input into TCDF. And other than that, it works the same way. You can make it so it's not going from left to right, or, I mean, like the furthest left to wherever you're looking at, because you can change what the lower bound is, but functionally it is the same as normal CDF, apart from the z-score thing. Okay. Any questions on that?
So the boundaries of the t-score?
What? What about them?
TCDF.
So they ask for lower and upper bound as the first two inputs. So you would do TCDF parentheses some number, comma, degrees of freedom.
But are those two numbers like for the lower and upper bound, the t-scores?
Those are the t-scores of the values that you're looking at, not what the values are. So if it was like, if I was looking at 30, I don't know, potatoes in a basket in a supermarket, it wouldn't be 30 potatoes. I don't enter that into my calculator. I find the t-score of what 30 potatoes is in terms of standard deviations, and then I put that in my calculator. Okay. Okay. So let's just do this one practice problem, because that's all I have. All right. We'll do it together. So we have sample size of 10 cars, right? Testing for gas mileage. And the mean of their gas mileage is 27.2 miles per gallon. So this is our sample mean. So it's 27.2. And the standard deviation is 1.8 mpg. Is that going to be expressed by sigma sub x bar, or is it going to be expressed by s? So is this the sampling distribution's standard deviation, or is it the sample's standard deviation? What do you guys think? Yes, it is the sample's distribution, or the sample's standard deviation, because it says the results of these 10 cars. It doesn't say the results of the sampling distribution, and it doesn't say that that's the population. Not the standard deviation of all of the cars is not 1.8, just those 10 cars. So we express this with S. So it's 1.8 mpg. And then 95% of cars have higher mileages than what value? So let's just write this statement as a distribution. 95% have a higher mileage than what value? So it's going to be here, because we want this to be the 95%. So this is 0.95. That's our probability. And we're looking for, this is the mean, what this value is going to be. So let's look at the criteria. What do you, we'll just assume that we know it's a t distribution, because it's pointless of me asking which one you should use, because we're talking about t distributions. So let's look at the criteria for a t-distribution. Alright. I forgot to put in this question, because I got it from somewhere else, that population is normal. So, what is the first criteria for t-distributions? Knowing that we can use a t-distribution to model this data. SRS. What's the second one?
Normal distribution.
Either it's a normal distribution or n is greater than 30. So, is n greater than 30? No. But population is normal, because that's part of the question. So, we're good to go because we can just say population is normal. Okay. What's the third one?
N is less than 10%.
Yep, n is less than 10% of big N. And this one we just assume because they're probably going to make more than 100 cars. So 4, what is the fourth one?
Standard deviation of population.
Yeah, because we only have the sample standard deviation, so we can't do anything with the calculating sigma sub x bar because we don't know what sigma is. So we're just going to say sigma unknown. That's all the work you have to show for the criteria. There's no weird like probability calculations like NP and 1 minus b. Unless you're dealing with proportions. Because you can model proportions with the t-distribution, but keep in mind you have to standardize it again based on t-scores and not your proportion standard deviation. So, we know now that it is okay for us to assume that this distribution we drew here is a t-distribution. So, we have p, we have n, and that's it. So, what function are we going to use here? If we have these two things, what function do we use? We have the probability, and we're trying to find the t-score. We use inverse t, because with inverse t, you go from knowing the proportion to knowing the t-score, and if you use t-CDF, then you go from knowing the t-score to knowing the proportion. So, we write it out as inverse t, or parentheses, then it's going to be proportion first. So we know it goes from left to right. So what are we going to put in the function? No, because it goes from left to right. 0.05. And the next thing we put in is degrees of freedom. What's degrees of freedom for this question? For this distribution? 9. 10 minus 1. And then we get something. So let's put it in our calculator. Second distribution for 0.05 and then 9. Paste that and we get negative 1.833. So what does this represent? Let's add another one. That's 1. Somebody explain to me what this represents. Carolyn, go.
It's a really mild curve. Or is it really?
What is? The t-score that I just calculated. What is that?
It's that much, like it's useful for t.
So, what does the question ask? Does it ask for a t-score, or does it ask for a value in context of the problem? So what do I do to that to make it the correct answer? t-score is x minus x bar over SE. And we want to know what x is because it's asking what value. And we know what x bar is because that's 27.2 from our sample. And we know what S is, but we don't know what SE is. So what do we do here?
You plug it in.
Plug it into what?
That formula.
So we plug in t is going to be negative 1.8331, and then we're going to solve for x, so we just leave it as x, and then we put in negative 27.2 here. What do we put here? Because this is SE, this is not S, because the t distribution is not the samples distribution, it is the sampling distribution, and the standard error is the sampling distribution's standard deviation, but we only have the sample standard deviation. So, yeah.
Put in the formula.
Which formula?
S over square root of n.
S over square root of n equals SE. So, we know what n is and we know what s is, so we can plug this all in. So, we'll get negative 1.8331 equals x minus 27.2 over, it'll be 1.8 over root n, or n is 10. So then we solve this for x, so we would get negative 1.8331, divide that by 1.8, multiply by 1.8, then divide by root 10, and divide by, just divide by root 10. So let's simplify it. We get negative 1.0434 equals x minus 27.2. So then we get 27.2 minus this number. And that gives us 26. Sorry, this should be x, not x bar. This is x. Because this is x bar. 27.2 is x bar. So then we get 26.156. Yeah. Does everybody get how I got from this step here and just did algebra? Anybody not get it? Okay. Anybody have questions about any of this? So you have to be really careful about what standard deviation you're going to use in this formula, because you can't use the sample standard deviation, because that doesn't work. Because the t distribution is the sampling distribution. We're representing what a sample size of infinity would be using our t distribution, because that helps us model what the population is going to be better than just the 10 cars that we got the data for. So that's why we have to use this equation, because this equation refers to the standard deviation of this, not the standard deviation of whatever histogram those guys made, because they only have 10 cars. Okay. Are we good with that? If you show all of this work, then that's probably going to get you full credit, I think. I'm wondering if it's overkill. No, I think this is what they expect you to show. You might be able to get away with less than it, but you shouldn't rate less than that. Also, when you answer questions on AP Stats, it helps the graders a lot if you write down what goes into your calculator, because then they know that you know what you're doing up until the calculator thing, and they can tell if you just beefed your calculator thing, and they will probably take off less points if they know that you just messed up the calculator thing. So from now on, if you're answering questions where you have to use a calculator function, just write out what function you were doing. So for this, it would be inverse t parentheses 0.05 comma 9. And then that would be good. Just have that equal whatever answer you get. Okay, so that's the end of the PowerPoint. We have half an hour left. So I understand that the fact that there are 3 different distributions and 3 different ways of solving problems because of all of these different things that I covered in day 6, that's confusing because sometimes you get a problem and you don't really know what to do because you're not sure which thing you should do because there's so many things to do. So I'm going to try to alleviate that by, that's the homework. Whatever. Okay. I'm doing a flowchart because I think that's the best way to express it. A flowchart of the thought processes that should be going through your brain when you see a problem like this. Oh god, I hate this word. Alright. So, the first thing that we need to look at is whether or not we're even looking at a sampling distribution. Because you remember the problems like the watermelon one that we did. Was it a watermelon? The warm up today? Like, that's not a sampling distribution. We just had the population parameters and we could just put that into our calculator and we're done. So the first thing that we must look at is, are we dealing with population or a sample? If the answer is population, then all you need to do is just do stuff with the population standard deviation and the population mean that you're given. So use population mean and population standard deviation. So that's the end of that step. Like, once you know that there's no sample that you're dealing with, that's all you need to do. You just use the things that they give you. But the moment they say you're taking a sample of, oh, by the way, if you're given a question like this, usually it'll say, it is known that the population of this thing has mean blank and standard deviation blank, and what is the probability that any given thing taken from the population's value will be greater than or less than something. So it's asking for what is the probability that one thing's value is whatever, right? So we're only looking at one sample that we take from the population. We're not looking at a sample that is of sample size 30 or greater or anything like that. You're just finding the probability of one thing, just taken randomly out of every person in the world if the population is people. So that's usually how they will phrase it. So let's say sample as the answer to this question. So then we must ask ourselves another question, because if we know that we're dealing with a sampling distribution, we have 2 possibilities. We can either use a normal distribution or we can use a t-distribution, which is what we covered here. So first question we should ask is, do we have the population standard deviation? Because if we know what the population standard deviation is, then we can just use a normal distribution, because using this we can find what that is using our formula. You good with that? So let's say yes to this. Then we must also ask, is n greater than 30? Because we have 2 situations where we will use a t-distribution. The first one is if we don't know standard deviation of the population. And the second one is if n is less than 30. Because if you remember on the slides, I said that you can use the t-distribution if your sample size is less than 30, as long as it looks relatively normal, right? So if we answer yes to this question, then we check the normality criteria. So this would be n is less than 10% of the population, and if you're dealing with proportions, then you do the p and p things. So n is less than 10%, np and n1 minus p, and then you also do SR. Well, we assume that all of these are SRS, because otherwise the question is kind of invalid. So these are the two criteria you must check if you know that it's greater than 30 and you know what standard deviation are. What if the answer is no for n is greater than 30? If our sample size is less than 30, then we must use the t-distribution. And so once we use the t-distribution, we must check if it's okay for us to do so. So to check if we can do that is we must have this also. So we have n is less than 10% of the population, and np and n times 1 minus p are greater than 10. So those are the two things that carry over from here because they're the same. If you're dealing with a proportion, then you must do np and n1 minus p. But we also must do additional things. If sample size is less than 30 for a t-distribution, what must we do to make sure that it's okay for us to use a t-distribution to model the sample? Yeah. So we have to check if either the data that we're given is normal or if the question says population is normal. So let's just say the question here will be given data. If you're given data, then you must draw a visual representation of the graph and check if it's normal. So a histogram would work, and a box plot would also work. So draw graph to check normality. And if you're not given data, then population must be normal. And so these, my handwriting is atrocious. Does anybody want me to read those again? Okay. So this introduces some issues because these are not hard facts. It might not say that the population is normal, and it might not say that, it might not give data that looks normal to us. So if we answer no to either of these, then we just say on our work that it doesn't meet that criteria, so we will proceed with caution because we're not sure if it's okay to model it with a t-distribution or whatever. Honestly, you could just say proceed with caution because we didn't meet that criteria. And that would be enough to get you points. Okay, any questions with this whole section? Okay, so let's go back up here because we never answered no to this. So if we don't know standard deviation, that is the other situation in which we should use the t-distribution. So if the answer is no, then t-distribution. And so we also must check all of these things because we're not totally sure if it's okay for us to use the t-distribution to model our data. So you basically just copy paste, okay, no, let's not. So here is n greater than or equal to 30. If you answer yes to that, then all you have to write is these two things. NP and n times 1 minus p. Because you don't have to care if the population is normally distributed if your n is greater than 30. Because that means your sample's big enough to assume that you can use the t-distribution. Because the t-distribution will fit any sample that is greater than 30 or 40-ish. But if you answer no to this, then you copy-paste this whole section here. So you must go through this process. So if n is not greater than 30, then you have to either check the data to see if it looks normal, or you check if the population is normal. If either of those things are true, then you're okay. If either of those things are not true, then you must say, didn't meet the criteria, and say which criteria it is, and then just say proceed with caution. Okay. Once you get to this point, where you figure out which line you end up with, you have to figure out which calculator function you need to use. Usually that's not too bad as long as you know what goes into each calculator function. So it's either going to be area or the z-scores / t-scores / like x that you're given. And once you do that, then you can usually solve the problem. So just remember that like the number one thing, like the first thing you need to think about is, am I looking at a sample here? Because on the quizzes, I saw a lot of people like writing down criteria for questions where it's only describing the population, and then they like erase the criteria, like, oh, I don't actually need that. Or they put criteria to things where you don't need them, and I'm not sure if College Board will take off points for that, but they might. And I think some teachers might, because it shows that you misunderstand the question. Okay. Does anybody have questions about this thought process? Raise your hand if you do. Okay. Does anybody have questions about the differences between a population distribution, a sampling distribution, and a sample distribution? Okay. Then, I don't have anything more to cover, but I do have 2 assignments. And one of them is a pretty short, just homework assignment. It's literally 1 page, and it's about t-distributions. And then the other one is a sample test that I found online for some stats teacher's class, so don't tell anybody that I'm using it, because that might be copyright infringement. But it's a little bit long. It's like 3 pages, multiple choice and FRQ. So I will be checking this, which is the t-distribution homework, on Tuesday, and then this practice test, which goes over everything until this lecture. So it'll be sampling distributions and normal distributions, but not t-distributions. So 2, 3. The thing I'm passing out right now doesn't have anything regarding t-distributions, but so no. Like, you take the entire pile that's oriented in one way.
So you take
Because-
like, you take the horizontal? Take all of it?
Yeah.
Oh.
So this will be due on Thursday, because it's a little bit longer, and I don't want to give you guys too much longer. All right. It is 6:12. So we have theoretically 18 minutes left. And do you guys want me to try to find more problems with t-distributions? Or does anybody have something they want me to go over? Or do you guys just want to, like, either leave or start your homework? Okay, so... What?
Can we turn the temperature?
I wish. It's really cold, but I don't control it, and there's no thermostat in this room. I'd have to ask.
I thought there was like a thingy outside.
Who's that? So it's set to it was set to 80 degrees, and then it said that the temperature in here is 65. So I think it's just not working.
When is the practice?
Thursday.
Good.
Okay, so next week we're going to start doing confidence intervals, and I'll just give you guys what an idea of that is, so it's a little bit easier to process, because I have a little bit of extra time. Alright, I'm gonna get rid of this. So, a confidence interval is taking the statement, I can be 95% confident that the population mean is going to lie between these two values. And the reason why this is useful, because if I have a sample mean, I can estimate what the sampling mean is, but that doesn't tell me anything about the population because my sample might be too small to be unbiased. So I could have just a sample that by sheer luck has everybody who's at the extreme end of one thing. So if I took a sample of 10 people, I might have an IQ result of 120 for their mean, just because I happen to sample really smart people. So I can do math to use the sampling distribution to give us an estimation of what the population mean could be. Because I can't just say, okay, the population mean is probably going to be close to my sample mean, and that's okay. No, that's not okay. So I have to be really particular about the wording. So this will be your sample mean plus or minus some value, we'll call it A, and then standard deviation of your sample. So that would be, or it would be standard error. So this is giving a range that is around our sample's mean, and we're saying that we're pretty sure that the population mean is going to be around this place. So A is what we're going to be calculating, and A depends on how big your sample is, because if your sample is bigger, then it's more likely that your population mean is going to be closer to sample mean. Okay, so that's the gist of what a confidence interval is. And it's just a really particular way of wording you just saying, I think the population mean is going to be around here because I took a bunch of people and that's what their average was. Okay.
Is it always 95% confident?
No, you can change that. And if you change this, then A changes. But this one and this one doesn't change because those are just what you get from your sample. Okay. Yeah, I don't have the lecture prepared, so I'm not going to go anything more than that. I just want to get you guys used to the idea of what it is. Okay, so it is 6:17, so there are 6:18, so there are 12 minutes left. If you want to chill here and do some homework and ask me questions, if you want, then you can. And if not, then you can go just be quiet about it.